Uh, Welcome everybody to today's seminar by Hersh Singh. So it's a very special feeling to have him on our channel because he was one of our ex-students, and especially he did his master's thesis with Suresh, and then his PhD advisor was also one of our alumni. Sorry, Sir Shailesh Chandrasekharan, who is at Duke, and so he will tell us today about how we can put asymptotically free theories on the lattice and some new developments there. Okay, over to you, Hersh.
Okay, well, thank you very much, Ayan. And I really want to thank Ayan and Suresh for this invitation. As he mentioned, I spent 5 really wonderful years at IIT Madras, and it's just really an honor to be back and speaking, even if virtually. It's just really amazing. So thank you very much. Okay, so well, yeah, let's get into it. So the idea that I want to talk about today is this notion of qubit regularization. I will define what that is, and in particular, we'd be interested in qubit regularizations of asymptotically free theories. So this is primarily based on this work with a little bit of these two, and these are all the collaborators. Sorry, I think there's. Okay.
It's okay, yeah.
I think we're good. Okay. Okay, so, well, we all know that quantum field theory is really important. It underpins the standard model of particle physics, right? It gives us electroweak theory, QCD, all of nuclear physics, and even in condensed matter physics, it explains critical phenomena. It gives us, say, topological phases of matter, and explains a whole bunch of things, right? So it's a very rich subject, and it's important in a whole variety of across disciplines in physics. But it's hard. Despite the enormous importance of these precise quantitative computations in quantum field theory, our tools for doing such are very limited. So, for example, we have perturbation theory, which is great for weakly coupled theories like QED, right? But it fails miserably for strongly coupled theories such as QCD at low energies in particular. On the other hand, we have tools such as lattice Monte Carlo methods, which can be used in some situations for strongly coupled theories. For example, you can use them for static quantities like computing the spectrum and so on. But again, it's limited because sometimes you just run into sign problems, and even this method fails. Or there are situations like out of equilibrium physics, real-time dynamics, and so on, where again you run into sign problems and the method doesn't work. But if you look at the history of quantum field theory, there's a way of looking at it in which developments in ways of doing numerical computations have paralleled new physical insights and new formalisms, right? So, for example, Feynman's diagrammatic methods can be thought of as as giving us a way to precisely compute quantities in weakly coupled theories, but then it also can be thought of as a perturbative definition of quantum field theory. And in the same way, Wilson's lattice gauge theory, coupled with his normalization group ideas, of course, enable very precise computations on classical computers, but then it also can be thought of as a non-perturbative definition of QFT. So you might ask, right, where do we go from here? How do we now approach questions like real-time dynamics of strongly coupled theories, where neither of these methods apply? And one possible answer to such a question might come from quantum computers. With the advent of quantum computing and some really amazing developments in hardware over the last few years, there's now a large push in simulating quantum field theories on quantum computers, right? And this is, of course, a really a long-term goal when it comes to something like QCD, but the efforts have started. And so it's interesting to ask, what is required if you wanted to simulate a quantum field theory on a quantum computer? Now, I'll be focusing on what is called digital quantum computers, right? Where you have qubits, and then you have these gates which you apply on qubits, and then that evolves the state of these qubits. In such a system, if you wanted to do say, a scattering calculation of a quantum field theory, you have a whole bunch of things that you have to sort out, right? At the very elementary level, you have to find an encoding of the degrees of freedom of your QFT onto the actual hardware degrees of freedom, which is qubits, and so on, right? So, of course, there are several steps in this process. I will be focusing on just the first one, right? There are issues. All the other steps are important and also, technically interesting. But one of the most important things is, how do you even map these degrees of freedom of your these quantum fields onto the qubits, right? And this is the thing that's being called by some people in the community as digitization. Okay, so what is the issue? Now, traditionally, if you consider lattice regularizations of field theories, right? So for example, consider like 5-4 theory or something, where you have a bosonic field, and you just write down a naive lattice discretization, like the one that's been studied using lattice Monte Carlo methods for the last few decades. This kind of a theory inherently has an infinite dimensional local Hilbert space, by which I mean it's infinite dimensional at each lattice site. And that's implied by just the commutation relations of the bosonic field variables, right? This algebra cannot be satisfied by any finite dimensional any finite dimensional Hilbert space. Okay, but that's a problem, because we're not going to be able to do infinite dimensions on digital quantum computers. We need a way of somehow truncating this infinite dimensional Hilbert space to a smaller one, and still be able to reproduce the physics of this infinite dimensional local Hilbert space in the right limit systematically, right? So that's the question of digitization. How do you do that? There is a lot of different approaches. There are a lot of different approaches that people have followed, and they all have to do, with what kind of symmetries you preserve, how, what space do you do this truncation in, and how do you get back the original thing, and so on, right? So this literature is just like enormous. It's growing very fast. There's just a lot of work happening in this area.
Hersh,
yes.
Can I ask something in
absolutely.
Naive question, actually? So, of course, for a gauge theories, the gauge degrees of freedom are really not observable in some sense, and then I understand the lattice. When you talk of the lattice, you're already talking about the gauge. It's already by manifestly gauge invariant formulation, right? So in this context, what if you put in some kind of a cutoff, right? Then there would be, you can still talk about a finite dimensional space in at least in given that you're discretizing the momentum too and many other things. So is it possible that you talk about, if once only look at the physical degrees of freedom?
So I mean, that's a good point. What you're saying is that there may be ways of formulating a gauge theory such that you have completely eliminated these redundancies of the gauge degrees of freedom, right? And in some cases you can do that. You can, like in 1+1 dimensions, right? There are you can often just completely eliminate the gauge degrees, it's completely integrate them out, basically, and be only left with the matter degrees of freedom. And and that's fine when it works. I think that's definitely okay. But there are two issues. One is that in general, you can't actually eliminate those degrees of freedom sort of analytically in higher dimensions. It's you know, if you I mean, the interactions are more complicated, right? So that doesn't work out. If it's a simple like a Gaussian or something, then you can do it. But if it's anything more complicated, then you're not able to do that. That's one issue. The second thing is that even if you integrate that out, you are still left with the other stuff. And if the other things are bosons, then you still have this issue of an infinite dimensional local Hilbert space, right? I think the cutoff, so when you said the cutoff, it's confusing because there are many cutoffs now. There's the usual cutoff, which is, say, on a lattice regulated theory, that is the lattice spacing. That's a cutoff, right? So that is the usual thing we do. But that still does not take care of the infinity at each lattice site. The fact that the local Hilbert space of any boson, even if it's a gauge boson or not, that space is still infinite dimensional, right? It's like a harmonic oscillator sitting at every
eventually when
site.
you take the continuum limit, yes,
right. So even without taking the continuum limit, there's it's an infinite dimensional thing. And then of course, the continuum limit brings more infinities in the game, right? Because then the density of lattice sites also blows up.
Sorry, could you explain why without taking the continuum limit, you still have an infinity? Didn't quite get that idea.
Yeah.
Okay,
so
maybe a very silly question that is.
Yeah, it's a good question. So
even for a real scalar field, we have R valued, right? It's valued on a line. Infinite number of values for the field, right? At any point.
Yeah, but we are discretizing the line, right? We are say into a set of
not
points.
Space, the field space.
The target,
field space. The target,
space.
the field space is itself. Okay. The field space itself is infinite. Okay, I see, of infinite extent.
Exactly.
Yeah, but I was thinking if you put some cutoff in the energy, isn't the field space also truncated? Like if you have if of course if there is no mass, then I don't see why. Okay, sorry. Okay, I see that. Okay.
Yeah. So mass, right? Putting a mass term is like a truncation.
Yeah.
You're right. And that can be thought of as a truncation in the field space. But that's a little bit trickier because then you really have to worry about the dynamics, right? Whether what configurations are suppressed. That's a dynamical question. Whether the mass suppresses these higher.
Okay. Thank you. Okay.
Yeah. That's a good question. Okay. So I was talking about this idea of digitization, right? This idea of truncation. Now, what most approaches that I mentioned in the previous slide, most approaches to digitization work in the following way. They start with a traditional lattice regularization, with the ones that have been studied in lattice field theory for decades. And then they simply truncate it in some way, right? And then they get this digitized model. And to get to the continuum limit, they have to start from the digitized model, take this limit first, which is the limit of the local Hilbert space going to infinity. And then, just like in traditional models, they, of course, also have to take the continuum limit. The question is this actually necessary? Do you have to do this two-step thing? Or can you start with the digitized model and just completely skip getting to the traditional lattice model? And it's actually sort of well known since Wilson that yes, it is possible to do that. And this is possible because of Wilson's insight that quantum field theories are, in fact, just second order phase transitions. In any lattice model with a second order phase transition, you will get a continuum quantum field theory close to that critical point. So, and this can happen even with finite, with in lattice models where each degree of freedom, each lattice site has a finite dimensional Hilbert space. So for example, spin models and so on have second order critical points at which you will get a continuum quantum field theory. right? So in that picture, right, to get a continuum limit, what you do is you have a quantum lattice Hamiltonian, and you tune yourself to a second order critical point, and that describes a very clean procedure to get a continuum quantum field theory, as long as you're tuned correctly. So in order to distinguish this idea or just this notion of getting the right quantum field theory without going through this traditional lattice regularization, we use this term qubit regularization. And that's all this means. It means start with a quantum lattice Hamiltonian, which has a second order critical point. And when you tune yourself to that critical point, you get the physics of your desired quantum field theory, right? And the crucial point here is that as long as you know that there's a critical point, you don't have to take this local Hilbert space limit. You don't have to enlarge the local Hilbert space. The critical point is in, yes.
Hersh, I still have a very naive question. Suppose you want to simulate some confining theory, right? Like UCD, then why you need some criticality?
Yeah, so the criticality is needed just to take the continuum limit. So the idea is, okay, actually I'll get to it in just a minute. I have a picture that might be easier to, maybe it's like yeah, okay, it's right here. So let me explain it using this. So okay, the question you're really asking is, how do continuum limits of lattice field theories work? Right? How do you take a continuum limit?
Well, no, actually, I mean, that is, I mean, what I was saying, that if you think of a confining gauge theory, and I forget about the gauge redundancy for the moment, right? It is like a massive theory. It's like some massive theory of glue balls or something. I can think of it as some gas of glue balls, or, and then I can actually have finite number. There should be a way to then digitize this, right?
Yeah.
So this is where I'm getting. You are basically talking about a limit where you have to take infinite number of degrees of freedom. So yeah, so that is where I was what I was saying, that if you really want to do something like a confining gauge theory, why would you need this?
Okay,
or maybe you're.
I think I understand. So maybe you're asking if the confining theory has a mass cap, or you know, say a theory with a mass cap. If the continuum theory has a mass cap, why do you need the lattice model to be critical? When criticality implies no mass cap.
That is what my question is here.
Yeah. So that's also a very good question. This is a question of basically units. And what's happening is, even though the continuum theory has a mass cap, the lattice theory in lattice units must be critical. And you can think of it in just in this way. So let me write it. If you have some physical mass, right? Physical mass is given by so correlation length in lattice units. No, sorry, 1 over that. 1 over A, where A is the lattice spacing, and then the correlation length in lattice units, right?
I don't see what you're writing. I don't see your writing.
Suresh, I can see that.
Oh, okay.
I mean,
okay. It's on the it's like here on top, right?
Maybe Hersh, you could
write in the middle.
Yeah. No.
Oh, how about this?
I think I'm on a phone, so.
Yeah, maybe Suresh is on the phone. Maybe you have to like say the equations in words. Yeah.
Okay, so but Suresh, you can see the figure in the middle, though, right? Maybe I'll just write in the middle. I think that might be easiest. So what I was saying is
I can see.
Okay. So M physical would be A physical times correlation length in lattice units, right? If M physical, the physical mass of the theory, is finite, and the lattice spacing goes to 0, then the correlation length in lattice units must diverge. Right? If A physical goes to 0.
Okay, now I understand. Okay.
Yeah. So this is just this is always, no matter what kind of continuum theory is, if you want to go to the continuum limit of a lattice theory, the correlation length must diverge, and therefore you must be close to a critical point. Okay.
Yeah, thank you. Thank you.
So good. So so this is just to explain this from a from the Wilsonian RG point of view. What's happening is, if you have this, let's say this line, so this space is this infinite dimensional space of all, all possible lattice Hamiltonians, and this line schematically represents a one parameter family of Hamiltonians, and this is, say, the traditional lattice model, right? This thing, and we know that this has a critical point. And when you tune yourself at the critical point, you're in fact on a critical surface, such that if you perform an RG flow, you will flow into this fixed point. And that fixed point is what governs the continuum, the physics of the continuum field theory, right? And the approach of digitization, one approach of digitization would be to just construct more of these models. Now, each of these might not have a critical point. So you can't directly take a continuum limit here, but you know that if you go first in this way towards the traditional lattice model and get the local Hilbert space right, then of course you will be able to take tune yourself to the critical point and get the continuum theory, right? So that is that approach. What we're suggesting is that for theories of interest, maybe you can just do this. You can just have the right Hamiltonian, which is constructed in a way that you sort of know that it has a critical point. And then you just directly do that, and you land at the same critical surface. As long as you're on the same critical surface, you only differ from the other regularization by just irrelevant operators, and you will still flow into the right fixed point, right? So this is the idea.
So Hersh, I'm a bit confused by this. So this critical surface that you're talking of, I think the point that you are describing is asymptotically free fixed point, maybe the traditional lattice model. That is what you mean, or and then what is this critical surface? Does each point doesn't represent any continuum limit of anything?
So each point on this critical surface represents the same continuum field theory. In sort of in like particle physics language, it's just that all of these are just irrelevant operators. Like this point and this point.
You mean
only differ
operators or irrelevant on the?
On the critical surface. So if you're exactly on the critical surface, then you're exactly critical. And that means that the long distance physics is just a CFT for all of these points, and it's the same CFT, and that CFT is a CFT of this fixed point.
No, that is right. Fine. But you drew. So you're not. Are you moving on the critical surface itself from one of these fixed points to another? So.
Yeah. So yeah, this
Sorry, I'm a little bit lost here.
There's a lot happening maybe in this picture. I should maybe try to simplify this picture. Okay, so there are two things. There are two things you could do, right? One is you could sit exactly at the critical surface, and once you're at a critical surface, there's another thing, right? There are two kinds of lines here. One line is these lines with arrows on it. The lines with arrows on it are RG flows. Yeah, I guess I didn't clarify this. So these lines are RG flows. So what I mean is this point is really an actual lattice Hamiltonian. And if you performed an RG flow of this Hamiltonian, you would flow into this fixed point. So that just means that the long distance physics of this lattice Hamiltonian is governed by this RG fixed point, right? The second thing that I'm doing,
if there is an error, but then you are not moving on the critical surface itself, right? I mean, you are moving out of the critical surface, I guess, because on the critical surface, you have only marginal deformations. You go from one point on the critical surface to another, you are there related by marginal deformations only, is it?
oh, maybe there's also this word critical surface has multiple meanings. I see. So let me define critical surface. For me, a critical surface is it's a critical surface because all points on this surface are lattice Hamiltonians which are critical, and they all flow into the same fixed point. So meaning that they actually all they are all related to each other by irrelevant operators. Now, what you're saying is also that can also happen, right? You're right that I can have also marginal deformations which take me to some other fixed point, but that's a scenario that I'm not talking about here. Does that clarify? I think there's, yeah, I see the confusion.
Yeah, I have to still understand your meaning of criticality here a little bit, but I think it is, yeah, I think you're talking of in a little bit different sense, which I don't quite digest. So
no, I in critical surface just means you've tuned the mass to 0 in a field theory language.
Yeah, okay. So the correlation length diverges, I guess.
That's all. The irrelevant operators are free. They're not determined by this tuning. So you can be at any point on the
fixed points, you are having some kind of a field theoretic description, I guess. I guess in this language, maybe. Right, Bala?
Sorry, any point on the critical surface represents a massless theory with some irrelevant operators. The fixed point has a very specific value for those irrelevant operators, where the theory is actually.
Okay. Thanks for the clarification. I see. Okay, so there are some irrelevant deformations that are existing, and it's still a massless theory, but with irrelevant deformations. But then you flow to.
That's right.
Okay, great.
Point. Yeah.
So basically, the critical surface is simply a surface of massless theories.
That's right.
Yeah.
Okay.
Yeah, with the same, all of which have the same low energy.
So there is no relevant operator here, essentially. There is no relevant operator. Yeah. Okay. Fine.
That's right.
Thank you.
Yeah. Thanks for that clarification. So the relevant operator is the one. Are these lines which take you out of the critical surface? So that's a relevant deformation. Just to clarify that a little bit.
Yeah, that is helpful. Okay, I was simply lost because I didn't understand what you mean by.
Yeah. Okay. Yeah, I think the figure. Okay. Thank you. Thanks for the question. Okay. So. Okay, maybe I can move on. Okay. So, well, now for a lot of QFTs, it's actually quite easy to construct such qubit models. For example, if you just think of the Ising model in 3 and 4 dimensions, that has the continuum limit of what in the continuum you think of as the 5-4 theory, right? So the 5-4 theory in 4 dimensions is just trivial, and that's in fact what you get if you tune yourself to the critical point of the Ising model. And similarly for d equals 3 dimensions, you will get the right field theory, right? And Ising model is of course just a spin half, a system of spin half degrees of freedom. So in a lot of cases, this is possible, and we all sort of know these cases. But the interesting question is, can asymptotically free theories be regularized in this way, where you start with only a finite dimensional local Hilbert space? And this, of course, is relevant from the point of view of quantum simulating a theory like QCD, right? Where it's not clear at all that you can construct given a qubit model, you can always try to find what continuum theory it gives you. But the other way is typically very hard. You can't, given a continuum theory, you can't just write down a qubit kind of model which will reproduce that. Right? That's a very difficult question. So for asymptotically free theories, it's not even clear whether this is possible, or if you really need an infinite dimensional local Hilbert space. And one of the challenges of asymptotic freedom is that there are actually multiple scales in the problem. So there's of course the lattice scale always in a lattice model. But then if you think of QCD, there is this exponentially large correlation length, right? It's the mass gap of the theory. So that's something like lambda QCD is here, right? So of course you want to get that physics right. That's the IR physics, right? But QCD is more than that, right? QCD tells you not just about the IR, but it really gives you precise predictions about the UV, right? It tells you what happens at quark scales, where at these short distances, the theory is supposed to be free, right? And there are very precise predictions. So there are all these scales, which are, which might be exponentially larger than the other, that you have to get right if you want to get the continuum limit of an asymptotically free theory. So this is, of course, I mean, other people have approached this problem, and there was this very nice idea which goes by the name of D theory, which was worked out in the late 90s, where you can achieve this regularization of asymptotic freedom by essentially extending the theory, essentially starting with the spin model with a finite dimensional local Hilbert space, and extending the theory in another dimension. And it's that additional dimension which sort of acts as a marginally relevant deformation that you need to get your mass gap and all of the scales, right? So this actually, I mean, this is a very, very nice idea, and it works. But then the issue is still sort of formally that it does require you to increase the number of qubits, because the size of this other dimension has to increase as you take the continuum limit. Even though you can show that, in some sense, the convergence is exponentially fast. So for practical purposes, you might not care about it. But still, right, the question remains, do you really need to do that? Do you really need to take this number of qubits to infinity? Okay. So to explore this question, let's talk about a well-known toy model of asymptotic freedom, and that's the O3 nonlinear sigma model in 1+1 dimensions, or 2 Euclidean dimensions. This model is, well, it can be described by this continuum action, where n is like a 3-vector that's constrained to live on a sphere. So it's unit 3-vector, and G is a coupling. So this is a very nice toy model for QCD because it has asymptotic freedom, it has dynamical mass generation, dimensional transmutation, all of the nice things that we like. Now, you can study this model using the following lattice regularization. This is what I'll be calling the traditional lattice regularization. And basically, it's just the naive discretization of the continuum action that we saw in the previous slide. If you just do that, and now beta is a coupling, you get this action. And now the question is whether this action has a continuum limit, which is a question of whether or not this is a critical point. And so I think this is now well established that, in fact, it does have a critical point in 1+1 dimensions. And the critical point is at beta going to infinity. And at that critical point, the correlation length diverges and you get a continuum field theory. And that's the continuum field theory that, I mean, you can define the O3 nonlinear sigma model by just saying that it's the theory which you get by taking the continuum limit of this lattice model, right?
Sorry, but this still has infinite number of degrees of freedom at each lattice side,
yes.
right? Because it's
yes,
okay.
exactly. So this this is what I'm calling the traditional lattice.
The traditional model.
regularization.
Okay, thank you.
Yeah. So this has exactly. So this has a problem, right? We can do it using classical computers, but for quantum computers, this is pretty bad, at least in the near term, right? Because you wouldn't be able to put this on a quantum computer at all. Just as a just to point out what the structure of the sort of RG flow looks like for this ON nonlinear sigma model in general D dimensions, right? Of course, we're interested mainly in the D equals 2 case, but there's also the D equals 3 and D equals 4. D equals 4 is just a Gaussian fixed point. Meaning that there's a critical point and which flows to the Gaussian fixed point. So what the continuum field theory you get is just the free field theory. In D equals 3, you have a very interesting fixed point. It's called the Wilson-Fisher fixed point, and this model in fact has a critical point at a finite beta, which gives you the continuum field theory associated with that. And
just Hersh, again, another thing I want clarification. I want regarding this diagram. So you are claiming that when you take the continuum limit of the lattice model, you will get into some massless theory, which may have some irrelevant deformations in it, and only the infrared you will be able to reproduce of the right critical of something. So is that the claim? So you don't know exactly what, you don't have really a control on which of this, where on the critical surface you are going to land, what you call critical surface.
I guess, are you asking, maybe I need slight clarification on the question.
So I'm just saying that you're taking some kind of a continuum limit, right? When you are taking a continuum limit of the lattice model, you will land on the critical surface, but not necessarily on the fixed point. Is it what you're trying to say in this? Yeah,
so, right. So that's certain. So yeah, the thing is that when you, for a lattice model, when you take the continuum limit, you have to be careful because you will always have, as I mentioned, you will always have the lattice scale in the problem, right? So there's always, in some sense, those irrelevant operators corresponding to these lattice artifacts, right? Because they don't change. Changing or taking the continuum limit for a lattice model is, in some sense, restricting yourself to large enough distances such that the lattice artifacts don't matter, right? And that's the same thing. In other words, it's the same thing as saying that the irrelevant operators have now become small enough under the RG flow.
Yeah, okay. No, this is again what I'm confused about. So you're saying that is it, so you're taking the so I was confused about this picture, maybe that. So you are showing this picture, you're taking a traditional model, you're taking some continuum limit, but you are not directly hitting the fixed point always. So this
you never hit the fixed point.
But I think maybe I get your point now. You're saying that if you're taking the traditional model with already infinite number of degrees of freedom, you are sort of bound to and hit the fixed point, perhaps, which you are calling the traditional lattice fixed point. But on the other hand, if you have some discrete degrees of freedom, and then if you might hit somewhere else on the critical surface, which has some irrelevant deformations in it, or I'm just getting lost by the picture when you're having
this is a very valid, these are very valid questions, and I think this is genuinely also because there's terminology that's different between different communities, and so a lot of my PhD was just like having arguments with people about these kinds of questions. So I totally understand your question. So what's happening is that there are also, because there are multiple lines, right? So in these figures, this line is on the critical surface, right? And this axis is going outside the critical surface. This is a relevant parameter. And when you tune a given lattice model to the critical point, meaning that you hit this point here, this will generically, or I don't know, I think this will never be the fixed point. This will be a critical point, which will be different from the fixed point by irrelevant terms.
So is this already the continuum limit or not? That's also another question. When you hit the critical surface, you're already in the continuum limit. That's the question, the first question that I have.
Yeah, so remember that yeah, so yeah, there are various directions we can make this statement. So we can say that to take the continuum limit, you must hit the critical point, but you have to take that limit carefully, and that's because, as I said, so we definitely have to. So maybe this is one way of looking at it. So we said that M physical is A physical, and then there's C lattice, right? And now if A goes to 0, then this has to blow up. So that's for sure true, that you have to be on the critical, you have to approach the critical surface to get the continuum limit, right? So that's true for sure. But how you take that limit, how you approach it, can change what continuum limit you get. And one way to understand it is the following. So if you imagine tuning yourself exactly to the critical point. So you first hit this critical point, and then you start looking at the larger and larger, the physics of longer and longer distance scales. If you do that, you will just get a conformal field theory. You will not get a massive theory, because you started at the critical point. So you were already massless, exactly massless. And so then there's no way you are going to get a mass from this theory. If you actually want to get a mass, you have to basically, this discussion gets, we can spend a lot. I think we can spend a lot of time here. Maybe I don't know if it's.
No, it's okay. I mean, you may go ahead and then, but yeah, I was just okay. My major confusion is in what is the difference between approaching a critical surface for a traditional lattice model and versus your qubit regularized models. So this is maybe
that thing has no difference. So that thing has actually no difference. There is no difference in how we approach that. That's what.
But then I'm also confused about when you start flowing out and when you start flowing in on the critical surface. What does it mean in lattice terms? Maybe all these things you are going to explain with some example, and then it will become clear. But let's then move on, maybe.
Yeah, I mean, I'll be happy. So I'll be happy also to stay for a bit after, because I think we only have 15 minutes left. Is that correct?
Yeah, so yeah, but 20 minutes, you can take 20 minutes, yeah, 20, 25.
Okay, so how about maybe we can come back to this question.
Sure. We can come back. Come back to it.
Yeah, I think this is a very important question. Also, it sort of goes to the heart of what we're trying to do as well. But let's come back to it. Maybe some of the things that I say will help frame the things better. Okay. So yeah, so here the main point that I wanted to make was that that this model, the traditional lattice model, in D equals 3 and 4 is also interesting, has been studied and has a continuum limit. And you might ask whether even in D equals 3 and 4, if you can construct this kind of a qubit regularization for the ON nonlinear sigma model, right? And actually, that's kind of easy. You just have to find that phase transition, meaning that you have to find a model where the symmetries are the right symmetries as you expect from the continuum theory, and then you can actually make that make the model have a continuum limit. And so this is what we did. I did in a couple of papers, one of them with my advisor, where we constructed basically the ON model with an n+1 dimensional Hilbert space at each lattice site. So we have a model where you can think of the local Hilbert space as being composed of one singlet state, singlet under ON. So let's just think of, you can think of it as just vacuum. And then you have the fundamental representation at each lattice site as well. So it's just the full Hilbert space is 1 plus n dimensional. And with that, this is just the Hamiltonian. For us, it doesn't matter what the actual Hamiltonian is, except for the fact that this Hamiltonian has this nice feature that you can construct a wall line representation, which can be very efficiently simulated or sampled in a Monte Carlo calculation using what are called worm algorithms. So this is like, just to give an idea of what's happening, you have the partition function, which is written as exponential of e to the minus beta h. It actually should be the trace here. And you can write that as a sum of world line configurations in space-time. And the world line configurations are configurations that look like this, right? So these are world lines of particles. And so particles which are charged under ON are sort of oriented world lines. And if you have particles which are not charged under ON, then they have this kind of a, then they're unoriented world lines. And the singlet states are just empty sites here, right? So the question then becomes just sampling these kinds of configurations, which you can do very efficiently thanks to worm algorithms. And you can show that, in fact, you get all the right critical exponents for this. So this is just a plot showing there's a critical exponent called nu, which is usually computed, and as a function of n for ON, we were able to show that this basically you were able to reproduce. You get good agreement with the other known results in literature, right? For example, this green line is a 5-loop epsilon expansion, and then there's large n. And all of these other methods seem to be in pretty good agreement. So that suggests that the 3-dimensional, the 4-dimensional models are easy to construct, and you can do that for large values of n. So this plot was d equals 3. So now we come back to the question of d equals 2, which was the really interesting one, where we have an asymptotically free theory. And to probe, remember, the question is always, how do you, how do you get not just the IR, but also the UV physics, right? So to probe the universal behavior of the continuum limit, there's a nice tool, which is called the step scaling function, introduced by Lucier, Weiss, and Wolf in 91. And this is essentially in some sense, a finite size version of the beta function. I'll define it in a minute as well. So to define it, let's put our theory in a box of finite size L. And this L now is your natural length scale. It's like a probe scale. The box is really small, you'll be probing the IR physics. The box is really, if the box is really small, then you're probing the UV physics of the theory. If the box is really big, then you're probing the IR physics, right? So let me skip some of the details. I'll be happy to answer, or if there are questions, then I can definitely get into it. But let me just say that just like you have the beta function, which describes, so G here is some normalized coupling of the theory. So just like the beta function defines or describes the change in the normalized coupling, if you have an infinitesimal change in the scale, the step scaling function does the same thing, but the change in scale is a finite scale transformation, right? So it's like L going to 2L. If L goes to 2L, G square L, which is the coupling, goes to G square SL, which is a function of the coupling at L, right? So this is just in some sense an integrated beta function. Okay, so just like that, you can also define, just like you have an integrated beta function, you also have integrated Kalin-Zemanzik type equations where you can ask what happens to a given observable if you change the scale by a finite amount. And it turns out that if you write down a dimensionless ratio of this kind, where the observable, so beta is a coupling, remember, and observable at length scale 2L divided by the observable at length scale L is again a function only of that normalized coupling. And what this function is a unique universal function, and it's in some sense a signature of your theory. You don't expect different theories to have the same function here. So as long as you can define,
it is independent of how you are qubit regularizing this thing.
Yes,
this function.
exactly. So this only depends on what continuum quantum field theory you get.
So it is should be true only in the limit when n goes to infinity, right? The number of degrees of freedom goes to infinity. Only in that limit, this should be same. This should be universality.
Right. So for the tradition, n by n you mean the local Hilbert space or the number of
the local
sites?
Hilbert space, yes, the local Hilbert space.
Yeah. So for traditional lattice models, if you were to just truncate it, then you're right. Then you will only be able to reproduce this kind of function if you took the n going to infinite limit. But if you have a genuine qubit regularization, meaning that even with a finite n, you can reproduce it. That's sort of the goal.
Yeah, but this looks a little bit very hard to digest because, for example, when we do matrix models or something like that, we do see the n dependence, no? And somehow only in the large n limit we see some universalities or sometimes. And so I'm a bit confused about why you are saying that even at finite n, we should be able to get these kind of, especially because in the infrared, you have large number of degrees of freedom, right? And of the continuum theory. So
yes. In this picture, right, what happens, so one way to think of what's happening is this the Kardanoff blocking picture, right, where even though you have individually look at the local Hilbert space is small, you can do this block spinning procedure and construct like these blocks of larger and larger sort of chunks. And those blocks now effectively have a larger Hilbert space, right? So this infinity, this n going to infinity limit that you're thinking of, that can emerge dynamically through RG. You don't have to put it in by hand. And that's what
you mean. Then you say that only in the infrared you will be able to get this universality for large L, or
yes. Yeah, so the word infrared is tricky because there are multiple scales here. So and what's happening is there is so I had this slide earlier where I said that there is some LUV and then there is L some maybe I just write this lattice spacing LUV LIR, right, which is like the correlation length or lambda QCD, 1 over lambda QCD, right? So the thing is, there is this IR scale, which is the genuine IR of the theory. Then there is this scale, which is the UV of the continuum theory. Then there is another UV cutoff, which is the lattice cutoff. So with respect to the lattice cutoff, everything else is IR.
Now, this I understand. And I also understand that LUV would be probably controlling this irrelevant deformations you were mentioning. And so this is probably
No.
you mean.
The irrelevant deformations I'm mentioning are actually this this lattice spacing. So at LUV, this entire region is supposed to be universal. And so
below LUV, below the scale LUV, that's what you mean. Yeah. Okay.
Or basically up, yeah.
Okay. Okay.
So
Below the
LUV
scale
is where you have
LUV
like
should
quarks.
Okay, that is
Sorry?
what you mean here. Maybe in this equation 10, it has to be L has to be less than LUV, right? That is what you mean. And in that, then in the continuum limit, you will get some universal function for L less than LUV. I think that's
Yeah,
what I
but
understand
so
from from this
I think
statement. Okay.
Yeah.
Thanks.
So LUV, what I want to say is LUV is a genuine physical scale. It's not a cutoff. It's a physical UV scale.
Yeah, I understand. I understand that. Okay. Okay. Thanks.
Okay. Yeah. Thank you. Yeah, those are excellent questions. Thanks for asking. So okay. So yeah. So the point here was simply that there is such a universal function that you can define and can measure in a lattice calculation, which is a signature of the physics in the entire IR to UV region. Okay, so let me skip this. This is just about how to exactly define how do we exactly define it. Let me not over that, but okay. So this is what this function actually looks like, right? So we define this function f of z, and so z is CL over L, and this is just another definition of your normalized coupling, right? So you think of the x-axis is just a normalized coupling, which is given by CL over L. C is the correlation length in a finite box L, finite box of size L. And on the y-axis is the actual function. So this is what this function looks like. When so if the correlation length is very, very large, or in other words, if the box is really, really small, then you're probing the UV physics, right? And so in that region, you're looking at UV, and we know that in in asymptotically free theory, in the UV, it's scale invariant, right? And if it's scale invariant, then a ratio of this kind, C2L over CL, will just be 2, right? Because that's what scale invariance does. There's no scale in the theory. So if the ratio, the only scale is L, so this is just 2L over L. So that's 2. That's why this approach is 2 in the UV. On the other hand, if the box size is really, really large compared to the correlation length, then you're looking at the IR physics, and that's what this region is, right? And in principle, you can access this UV region using just perturbation theory, because we know perturbation theory works in that region, whereas the IR is harder to get from perturbation theory, but that's where typically lattice calculations are done. Okay, so let me skip some of this. This was just to show that there are in fact models that we can write down which get the right IR physics. So look at all of these points. They're all like perfectly falling on this curve in the IR, but you can't get points in this region at all. So you simply are not able to get the UV physics right. But you can get the IR physics as long as you get the symmetries right. So somehow it's easier to get the IR physics correct as long as you have the symmetries right. And that's sort of the effective field theory point of view, is that, right? As long as you write down, you have the right symmetries, and you write on the most general Lagrangian with that symmetry, at low energies, only a few things will dominate. You get the right thing automatically.
So this is because you have landed on the critical surface, but not on the critical point, because you have some LUV in this, which you. So beyond the scale LUV, your theories differ. Different theories on the critical surface are not the same.
Right. So from that picture, what's happening here is something like this. So there is a critical point. This is a true critical point that we actually want to reach, or maybe a critical surface, for example. Sorry, something happened. Okay. So this is a critical point. I'm just going to call it lambda c, let's say. This line represents the critical surface, right? So this is a fixed point. What's happening here is that as we tune the Hamiltonian, we don't actually land here. What we do is sort of go past that and don't even hit the critical surface at all. So we are able to go close to the critical point somewhere here. But if you're not at the critical point, then correlation length does not diverge, right? It's finite. And that's what is happening here, right? So what's happening here is that there's a finite value of CL over L, and you're not able to increase CL to infinity, which should happen if you were actually at a critical point. Right? If you were at a critical point, you should be able to go all the way to the right of this plot, because CL can be made arbitrarily large in that case. But here you're not able to do it. So we just don't find the critical point in these models.
And what is the y-axis here?
Yeah, y-axis is CL, C2L
by
C.
Okay.
L. So this was the definition of the universal
scaling,
step scaling function. Yeah. Okay. So yeah, so since I'm out of time, let me just quickly say, so let's skip all of this. Let me just say that we tried a whole bunch of things. In a lot of these cases, you get the right IR physics, but are not able to get the UV physics in the same way. And finally, we tried this model, which we call the Heisenberg Co. And this is a spin half model where you have this chain, and then at every side you have coupled with another qubit. And for this model, in the limit of this coupling going to infinity, you in fact find that the universal step scaling function is reproduced. So you see that these, this is for some j equals 3, that coupling. Then you increase j to 5, you are able to get in this region. And then you increase j to 10, you are able to get even this region. And I also show the perturbative thing here. So this line here, that's the perturbative line. So you see that this entire region is already in the perturbative region, which is sort of the UV. And the fact that this model reproduces this step scaling function is pretty strong evidence that, in fact, that this has the right continuum limit. If you actually look at the correlation lengths that are achieved in this region on the right, that's like 10 to the 5 in lattice units. So that's huge from a lattice calculation point of view. That you get UV physics up to these large scales. Okay, so I think that brings me to the end. Maybe I will just say that there's a notion that seems useful to define for doing quantum field theories on quantum computers, and that's this notion of qubit regularization, where you can try to achieve the continuum limit of a QFT even with a finite dimensional local Hilbert space. But it's not clear whether this is possible for all QFTs. We were able to show that this seems possible for the two-dimensional O3 sigma model, which is an asymptotically free theory, which is quite encouraging from the prospect of simulating QCD eventually. And the sort of space of such non-traditional formulations of lattice field theories, I think is extremely rich, and there's a lot of stuff that can be done with these kinds of models, which I did not have time today to talk about. But they're certainly very, they could prove very important for near-term quantum computers, just from a resource scaling point of view. So I think that's it. I'd like to thank these people and the funding agencies for support on this work. And thanks very much to the organizers for having me. I'll be happy to take any questions.
Yeah, thanks, Hersh. It was a very interesting talk, and it was a very interesting. It's a great work, also really very impressive. It is still it's like really pulling this model out of the magic wand. It seems, but it's very interesting indeed that it works. So, any question to Hersh? Okay, so so it seems that you have been able to guess this qubit regularization out of the hat in a way. I mean, was there a systematic way you could have guessed that this Heisenberg-Bohm model would have worked for the NLSM?
Yeah, that's a very good question, and unfortunately, I have to say that there isn't, as far as I know, a systematic way to find that. For us, we really had to try a whole bunch of things, and there was some intuition that there's things like symmetries that guide you, certainly, and which are very important to get the right theory, and certainly, and then there's intuition, but there isn't really a systematic way to get it, and I think that's kind of the challenging and sort of also the interesting aspect here, right? That it doesn't really tell you, for example, if you wanted such a regularization of QCD, where you could really formulate QCD in terms of qubits at the fundamental level, right? That would be pretty interesting. And now this doesn't tell you that it should be possible to get that kind of a regularization of QCD. But
but suppose if a question somebody asks you, like, suppose I ask some of them program a quantum computer to look into all possible such discrete models, defined with using some symmetry, and try to find out what kind of continuum limits it gives, and then somehow by look at, so is it in principle possible? And there was some result I read that this problem is undecidable, to say which of these models will have a mass cap or which will not have a mass cap. If you take some kind of discrete model of this kind and try to take the continuum limit, then there was some recently, it has been proven that it is undecidable. I don't know whether it's an undecidable in the quantum computing sense or quantum algorithm sense, or in the
I did not,
or in the traditional algorithm sense. But
that sounds very interesting. I didn't know if there is a you're saying that is a result about continuum limits of such models.
Yeah,
That's
I think it was a few years back. It was been proved that this is an undecidable problem. Just to take any kind of lattice theory and try to take a continuum limit, the question is whether this will have or not have a mass cap. That is an undecidable problem. That's the result, I think.
I see. And so those kinds of results are typically for generic, right? Generally, it will not be. But of course, in special cases, we know, like sometimes we can exactly solve the model and so on. So that seems about. It seems like in general, it's a very hard problem. You're right that given an arbitrary Hamiltonian, you just don't know anything about it, and no technique will work, because Monte Carlo will have a sign problem, quantum computers will have some, so yeah, I think yeah, really the question of how to systematically search, in some sense that's what we did. We restricted ourselves to this 2-qubit subspace. So we restricted ourselves to like the most general 2-qubit Hamiltonian that you could write down, and then explored that. And I mean, a lot is known in the condensed matter literature about that, those models, because in some limits you'd get a spin 1 chain, in some other limit you have a spin ladder, and these models have been studied. And so it's also known that there are a lot of critical points. There's a lot of interesting critical points in this model, but none of them is or as far as we found, that none of them was the asymptotically free critical point that we wanted. So then it's just a matter of how do you have the, I guess, right intuition or something.
So your claim is that here there is no LUV when you take the continuum limit, at least in the limit when capital J goes to infinity. The LUV vanishes and you're able to reproduce the entire asymptotically free theory.
Oh, I would say LUV goes to infinity.
That's exactly, so that's exactly what I meant. So LUV doesn't exist, meaning that LUV
exactly. So you are able to reproduce precisely, right? So
yeah, we reproduce the entire theory in this
exactly
in the limit when capital J goes to infinity. That's the claim. That's a remarkable result. Yeah, that's quite remarkable. Yeah. So, but I'm still a little bit. So, if you keep a finite J, basically you have you are basically having some LUV, right? In the theory, and
exactly.
I see. But it might be also useful to understand what kind of irrelevant deformation of the original theory you're having, right? Because that if you understand it systematically, then that is also a good thing, because you literally don't need to take J goes to infinity.
So, I think you are saying, I think what maybe another way of saying what you're saying is the effective field theory point of view, right? That
exactly, which are the movement on the critical surface, which what you showed. If you could systematically track which kind of irrelevant deformation where you're flowing, or what exactly the flow that is being triggered by change in J.
And that's true. I think that makes sense, but I think that numerically those kinds of things are hard to do, to actually match an effective these coupling constants of an effective field theory to a lattice. I mean, can be done, but it's especially in this kind of a thing where the scales are so huge.
It's very challenging.
And the other question is, whether in some sense, the question of getting the UV physics right from a lattice calculation, you could say, is kind of an academic question, because you would never use a lattice calculation to get the UV, right? Because you can just do perturbation theory. Why would you do that? You would really use a lattice calculation to get the IR physics.
No,
and in that case,
I disagree, because suppose if you're doing a real-time simulation, then there is a UV IR mixing, and I don't think often you could separate this out in a meaningful way, because I mean, there is interchange of energy from UV to infrared scales, and in a dynamical situation, right?
That's fair. That's fair. That's fair. Yeah, that's fair.
So you can have UV cascade, IR cascade, all kinds of energies cascade, and so there is. So you need to get the full thing right, I guess, if you have to talk about time evolution.
Yeah, that's interesting. I hadn't considered that you can see this mixing in dynamical situations.
Yeah. Especially when you look at longer time scales. I mean, so if you look at longer time scales, this mixing becomes more important, right? Because so one simple example is that you can put you can put an electric field, a constant electric field. A thing will accelerate, And then even if you start with low energies, you go to very high energies over a certain period of time. So so then you will miss the physics. If you do not get the UV right, then the time evolution you get is different. Will be
That's right. That's right. So from an effective field theory point of view, you would have to say that I'm looking at these time scales, and my effective field theory is only accurate up to this scale. So I can simply not ask questions beyond some time scale or something like that. Right?
Yeah.
And
yeah.
Yeah.
So it will work only for certain times, unless you get the UV also correct. Yeah.
Yeah. Right. And so yeah, that sounds totally totally right. And like it's possible that even in those situations, practically, that you only have, you only want information up to these energy scales. And in that case, any of these other models that I showed, where they're getting IR physics right, any of these other models might also actually work, right? As long as this is where the information that you said, where you have a good effective field theory description, in that what is the right, what is sort of the cutoff of the EFT and so on.
So if you feel for every J, the corresponding EFT, that would be then also a good way to reinterpret it and understand it. Yeah. But that, as you said, it's very hard, because to map local operators to the lattice is not easy.
That's
very good. Yeah, excellent. So it was a great, I really enjoyed the talk. Thanks for your time. And and hope to see you in IIT actually, then whenever you're back to India.
Oh, that would be so awesome. I would love to. That would be, whenever I visit, I don't even know when is it. Right now, all travel seems a little bit.
So currently in the audience, there is Tanay, who also is a 5-year student, who was a 5-year student. He's now, he's now here.
So,
you can say.
Hi, Tanay. So you are now a 5-year student, or?
No, I was a dual degree student, but now I'm a graduate student in the same department.
Oh, nice.